In this video, I will explain how do we understand a frame structure or a truss structure is stable or unstable or unstable. Let's read first what is stability. This is a part of my book, Structural Mechanics and Analysis. It will be published soon. Actually, I made some revisions, and except grammatical errors, I think my book is now erroneous from the standpoint of theory and application of mathematics. Now let's read what is stability. In simple terms, stability means that the structure does not collapse. So if the structure does not collapse, the structure is stable. If it collapses under an arbitrary load or load group, then the structure is unstable. Okay. Then how do we understand that the structure can collapse or not collapse under any arbitrary loading? Then if we can give the correct answer by means of methodology to understand that a structure does collapse or not collapse under arbitrarily chosen loading, then the method shall be perfectly defined here. In civil engineering, a stable system or a stable structure means a system that does not collapse under arbitrarily chosen loading. The opposite of stable is unstable or unstable. To understand the meaning of stability, this video can be watched. This video you can find also in my YouTube channel. Since only one-dimensional load-carrying members, these are the frame members and the truss members. Truss structure is composed of truss members. Frame structure is composed of frame members. So member is a component of structure. These one-dimensional load-carrying members are within the scope of this book. Stability is explained only for structures composed of those members. You can also see one structure is composed of frame members and also truss members. This can also be done. In the way of stability, a one-dimensional load-carrying member is a continuous element between its beginning and end points. Its cross-section dimensions are very small in comparison to its length. Now you see here its length, and you see its thickness, width is very small in comparison to its length. Or here, this is a frame structure example, this is a truss structure example, you can see that. If a hinge is added to one-dimensional member, this is the abbreviation of one-dimensional member, the one-dimensional member is divided into two one-dimensional members at that hinge point. For example, if here there was no hinge, we had just one frame member, one-dimensional frame member, but because of that hinge, since the hinge divides the element into two, we have 1 and 2 here, two one-dimensional members. One-dimensional member systems are classified in figure 2.6 from the standpoint of stability. Okay, one-dimensional members. Stable one-dimensional members and unstable one-dimensional, not the member, structure, or let's say instead of structure, system. One-dimensional systems are divided into two, first of all, stable or unstable or unstable. Then stable structures are determinate systems or indeterminate systems. Unstable systems are divided into two again. Instability occurs because of deficient supports, or instability occurs because of wrong chosen supports. Okay, so first of all, we have to understand what is determinate system and what is indeterminate system. Okay. If a one-dimensional member system is composed of frame members, then the internal forces, moments developed in the members are normal force, shear force, and bending moment. For that system, if all frame members satisfy the equilibrium equations, we have three equilibrium equations for determinate systems per member. For example, here I have one member, here I have one member, here I have one member. But here I have two members because the member divided the member into two. It creates two members. Okay. For frame systems, for those elements, not those elements. These are truss systems. For example, for this system, we will apply, there is just one member. So we have three equations. These three equations can be those or those. Okay. And here, this is the equilibrium of forces in horizontal direction, equilibrium of forces in vertical direction, and equilibrium of moment about any point. At this point must not be a point which is on the member. It can be here, here, or here. Okay. If all those three equations are satisfied for this member, then our system is determinate system. Can be solved by means of those equations. Or we can make the check if this member or all the members are whether all the members satisfy equilibrium equations. We can use these equations. Here in these equations, there are two moment equations, equilibrium equations, and the points can be taken again anywhere, but they should be different. Point 1 is, for example, here. Point 2 is, for example, here. Or point 1 is here. Point 2 is here. Anywhere outside the beam. And then any horizontal or vertical direction, this equation shall satisfy. But actually, it is important that, for example, instead of horizontal and vertical directions, any arbitrarily two directions can be chosen. But these two directions have to be perpendicular to each other. For example, I have here two members, and one member shall satisfy three equilibrium equation, this one or this one, and the other member shall also satisfy three equations. Okay, so the number of unknowns, if the number of unknowns are equal to the number of equations which are required to solve the system, then the system is determinate. For example, I have here one member, two members. Per member, I have three equilibrium equations. So, since I have two members, 2 times 3 means 6 equilibrium equations I have. So, the number of unknowns in the system shall be equal to 6. Here, let's count the number of unknowns. 2 reaction forces here, 2 reaction forces here, and 2 common hinge forces here, which makes 6. So number of unknowns is 6, and number of equations is 6. So the system is determinate. I am speaking now for frame structures. So determinate frame structures are those which can be solved using 3 equilibrium equations per one member. For truss members, the internal forces developed in the members are only normal forces. No shear force, no bending moment for truss systems. or for truss members. For example, for this truss member, we can speak only a normal force. For that system, if all truss joints satisfy the equilibrium equations, these are the two force equilibrium equations, and all internal forces can be solved solely with the aid of equilibrium equations, then the system is determinate. See figure 27b. That's the 27b. These are determinate truss systems. As you see here, we see the basic truss system composed of only 3 elements, and then always 2 elements is added to the system to create different determinate truss systems. We take this basic shape and add again 2 elements and create new determinate truss systems or truss structures. To be able to solve the determinate frame system or structures, their carrying scheme must be drawn. Scheme or schema? Let's check it. Sorry about my English.
Schema.
Schema.
Schema. Schema.
Schema. Let's say schema. This schema shall be drawn to be able to solve the determinate frame systems. Their carrying schema must be drawn. Carrying schema must be drawn. For that reason, first every member is separated from its ends, which are hinge or support points. For example, this is the hinge point, this is the support point, this is the support point. So this member has one hinged end, one supported end, and this member has also one supported end and one hinged end. But both ends may be supported or maybe, as you see here, hinged. Then a free body diagram of every frame member is drawn. It thus becomes evident where to start to solve the support force moments and the member internal force moments. For instance, if the frame shown in figures 2.8, that is figure 2.8, the Gx and Gy support forces are solved first from the member carried, then those forces act on the carrying member as if they are external loads. The examples of drawing carrying schema are shown in the consecutive figures. Now, let's just concentrate on this example. Here, as you see here, this is the carried member. If this is the hinge point, so one member is here, and the hinge is actually constitutes or behaves as a simple support here to support the loads acting on that beam on that frame member. But the reaction forces occurs here are transferred to that member as external loads, as if they were external loads. So this member actually carries this member. If you divide the system from their hinges, you will understand which is the carried member and which is the carrying member. Which is carried and which is the carrying member. First of all, we spoke about frame members. Now continue on speaking frame members. Look, there should be an important part. Let's read this important note and consider this example here. The frame structure system, there are always exceptions. Given in figure 210, figure 210 cannot be divided into two separate structures. Here, because both frame members carry the load together. In other words, there is no carried member. Both members are carrying members. So this is also carrying member, this is also carrying member. Therefore, both members are considered first degree indeterminate structures. Nevertheless, they can be solved using equilibrium equations because the two unknown hinge forces are common unknowns. The proof is as follows. If I look here, this is one member, and per one member, for a determinate system, there shall be three unknowns. But I have for this member 1, 2, 3, 4 unknown. And for this member, I have 1, 2, 3, 4 unknown. Okay. So the number of unknowns makes 8. But however, the two of the unknowns are common. So from 8, the number of unknowns reduces to 6. And 6 unknowns I have. And both are carrying members. Unlike that one. One is carrying member, the other one is the carried member. Okay? This is an exception. And the number of equilibrium equations written for the system is, I have two members, and for one member I can write 3 equilibrium equations. 2 times 3 makes 6, so I can write 3 equilibrium equations, and number of unknowns is also, number of equations, equilibrium equations which can be written for 2 members is 6, 2 times 3, and the number of unknowns, now 2 times 3 makes 6, so the total number of equilibrium equations which can be written for the system is 6. And the number of unknowns is 6. Since they are equal, they shall be equal, not greater, not lower. Okay, they shall be equal. So this is as a result, this is a determinate system. But an exception, because you cannot draw a load carrying schema as you see here, or as you see here. Here we have one carried member and one carrying member, and others are carried and carrying members. Okay. Here in these examples you see, but you cannot put, if you compare the two members with each other, you cannot put one above the other, because both of them are on the same level. Both of them are carrying members. This is an exception. And this is a special example. This is determinate. Now, put this figure in your mind, memorize it. This is a determinate structure, and it's stable structure. All determinate structures are stable structures. Determinate structures. And all indeterminate structures are also stable structures. Unstable structures are also divided into two, but they are not determinate nor indeterminate. They are just unstable. Okay? Because of two reasons, this reason or this reason. Now let's continue. And coming, unstable. Indeterminate structures. Indeterminate structures. Sorry about that. So order might be different. Doesn't matter. If one reader complete the whole, he will understand everything. indeterminate structures. For frame structures, indeterminate systems are systems in which the number of total unknown support forces, moments, or hinge forces is more than the number of equilibrium equations written for the whole system. Number of unknowns is greater than the number of equilibrium equations written for the whole system. Okay? Now in the examples we will understand the meaning of this sentence. I will clarify it for you. By means of these three examples are enough. The total number of equilibrium equations is 3 times the number of frame systems in the frame structure. For the truss structure, indeterminate systems for frame structure, for example, number of equilibrium equation is here 3. 1 member times 3 makes it 3. Here these are supports, but the hinge does not cut the member into 2. So the beam is continuous. So there is just one member here. You can see if you calculate the moment and draw the moment diagram, you will see that the moment at that point is not 0. Okay? So this hinge is different and this hinge is different. Okay. Here I have also one member and just 3. In all those systems I have just one member, and for one member I can write 3 equilibrium equations. The number of equilibrium equations written for all of these three systems is always 3. But the number of unknowns, 1, 2, 3, 4. So number of unknown is 4 greater than 3. So this is indeterminate system. As you understand, indeterminate systems are better than determinate systems. But solving them is harder than solving a determinate system. Here, number of unknowns, 1, 2, 3, 4, 5, greater than 3. So this is also indeterminate system. Here, number of unknown, 1, 2, 3, 4, 5, greater than 3. So this is also indeterminate system. Another example, number of unknown is 6, one member, so 3 equilibrium equation. 6 greater than 3, so this is also indeterminate structure. Here I have also just one member. This is not a hinge. It's a support. Okay? So 3 equilibrium equations, but number of unknowns are too much, which is greater than 3. Here there is a hinge, here there is a hinge. So I have 2 members, 2 times 3. I can write 3 equilibrium, 2 times 3, 6 equilibrium equations. Number of unknown is 3, 2, 5, and 2 here, 7. 7 is greater than 6. So this is also indeterminate structure. Here number of unknown is 3, 6, and 2 here, 8. 8 is greater than 2 members. So 2 times 3 makes 6. 8 is greater than 6. So this is also indeterminate system for frame structures. So for the truss structures, let's define the indeterminate truss structures. For the frame structures I did, the total number of equilibrium equations is 2 times the number of hinges in the truss structure. Moreover, those systems are stable structures. Examples of indeterminate system of frame and truss are given here. Okay. The same rule applies here. Let's count the number of equations which can be equilibrium equations which can be written for truss structure. For truss structure, I calculate the number of hinges. These points are also hinge points. 1, 2, 3, 4, 5. I have 5 hinge. For every hinge, I can write two force equilibrium equations, one horizontal, one vertical. Or in any two directions, but which are perpendicular to each other. So 5 times 5 hinges times 2 makes 10 equilibrium equations. Now let's count the number of unknowns. 2, 4, 6, 7, 8, 9, 10. Did I make there is a mistake here. Sorry, I forget, I made a mistake. The number of equilibrium equations is 5 hinges, and two force equilibrium equations are written for each hinge. 5 times 2 makes 10 equilibrium equations. Now let's calculate the number of unknowns. Number of unknowns are calculated so for a truss. First of all, these I have 4 reaction forces, support reaction forces, and the member forces are also unknowns. So how many members do I have? 1, 2, 3, 4, 5, 6, 7. 7 plus 4 makes 11 unknowns. So 11 number of unknown is greater than 10, which is the number of equilibrium equations. As a result, this is also an indeterminate truss structure. For truss structures, we did so. Let's come back. Let's go to page 34. I apologize for because of my English. I have corrected my pronunciation 2 weeks ago, but since I didn't speak English I haven't spoken English for 2 weeks. I lost my better English, American English pronunciation ability. Now unstable. Now as we know from the schema, I have told you determinate and indeterminate one-dimensional systems, frame system or truss system. So we have learned those systems, and both of them are stable systems. So unstable. An unstable system, frame or truss, can occur because of deficient supports or wrong chosen supports. Just examples will be given. Let's come to page 34. Unstable or unstable one-dimensional member systems. Unstable systems are structures the rigid motion or rotation of which cannot be avoided under an arbitrarily chosen loading. Arbitrarily chosen loading. Unstable systems because of deficient supports. This is easy. This is easier to understand. For frame structures, such systems occur when the number of unknown is less than 3 per member. Easy to understand. I will just count the number of equilibrium equations, the number of unknowns. If the number of unknowns are less than number of equations, then because of deficient supports, the system is unstable. That's okay. For truss structures, such structures occur when the total number of unknown is less than the double the amount of all hinges. That is, the double the amount of all hinges is also the number of writable equilibrium equations. Example of systems that are unstable because of deficient supports for their frame and truss structures are shown in figure 217A and B respectively. Now let's check here. We will understand how the instability occurs because of deficient supports. Here you see I have one member. I have one member So 3 equilibrium equations I can write. 3. But the number of unknown is 2. So 2 is less than 3. This is unstable because of support deficiency. This is also a same example. This is also a same example. Here I have two members. So number of unknown is 2 times 3, 6. Number of equilibrium equations, 2 times 3, 6. Number of unknown, 2, 3, 5, less than 6. So this is unstable because of support deficiency. Okay. Further examples are given. Now you see this is apparent. One support is taken from a determinate system and it became unstable. Here you see one support must have been a simple support instead of a roller, but here both of them are roller supports, so it becomes unstable. Let's calculate the number of equilibrium equations. 1, 2, 3, 4, 5 hinges. 5 times 2 makes 10 number of equilibrium equations. Number of unknowns, 1, 2. These are the reaction forces, and then I will continue counting the member forces, the normal forces in the members. 3, 4, 5, 6, 7, 8, 9. So 9 is less than 10. So this is an unstable structure because of support, deficient supports. And similarly. Now deficiency might occur because of wrong chosen supports. There are enough supports, but they are placed wrong or wrongly. They are placed wrongly. So because of wrongly chosen supports, the system becomes unstable. For frame structures. In frame structures, instability in such systems occurs because incorrect supports are chosen when the number of unknown support hinge force moment is equal to or more than 3 per member. We will understand this sentence. I will clarify here. I will clarify the meaning of this sentence over those examples. To check whether this kind of instability exists in the structure, Px, Py, and in P external loads, these are arbitrarily chosen external loads, are applied to the whole structure. This is the method given here. This is the method I prefer to check if the frame system is unstable or stable. The equilibrium equations per member, as we previously we have seen, those are then written for the whole system. If equilibrium equations are not satisfied, then the structure is externally stable, not per member. We write 3 equilibrium equations first for the whole structure. If they do not hold, then the structure is externally unstable. If equilibrium equations are satisfied, then the members are separated from their ends and equilibrium equations are written for every member. One member has 2 ends. Here end means a support joint, a hinge point, or a free point. If equilibrium equations are all satisfied for every member separately, then the structure is stable. If not, then the structure is internally unstable. Examples are given here. As you understand, to understand if a structure is unstable because of wrong chosen support is harder to understand than the structure is unstable or unstable because of deficient number of support. For example, we have here 3 supports and 3 support forces, so the number of unknowns are 3. This is not a hinge. This is the member is continuous here. This this is an intermittent support, let's say so. So there we have one member. So number of equilibrium equation is 3, number of unknowns is 3. They are equal. So there is no lack of support. But however, the supports are chosen wrong. If we write, for example, horizontal force equilibrium equations, you will see that it is equal to Px, and Px can be chosen arbitrarily by myself. Can be 5 Newton, 10 kilonewton or something, which might not equal to 0. This condition can occur. So, for any arbitrarily chosen horizontal external load, the horizontal force equilibrium equation might not be 0. As a result, this is an unstable system. Mathematically, we can understand if one system is stable or unstable. Here, another example. Now the roller is rotated 90 degree. One can say that what is the difference? But the difference you will see now. These are arbitrarily chosen loads, one horizontal, one vertical, and one external moment. These are the reactions which are given in the picture with blue color. Now let me write one moment equation about point A. You see, and you see this force passes through point A. But this is an external moment, and this force is an arbitrarily chosen load, does not pass through A. And there is a plus here. So think that all values are positive, and it is not equal to 0. So the moment equilibrium equation does not hold for many arbitrarily chosen loading. As a result, this system is mathematically it is proved that unstable because of wrong chosen support. This support shall not be rotated 90 degrees. Now here another example. We see we have again 3 supports, but as in this example, and 2 of them are rotated 90 degree. And now in this time, at that time, I write moment about point B. You have to understand this by yourself. It's harder to understand. For example, there might be some loadings, arbitrarily chosen loadings, for which these 3 equilibrium equations hold. You have by experience understand and choose some Px, Py, and Np loadings, so that, and you shall understand the equation does not hold for this type of loading. As a result, the system is unstable. Now, for this type of loading, moment about point B is, as you see here, Np, this force passes, and this force, Px here, passes through B. So Py and Np creates moments here. But there is minus here. But for example, think that Np is very high in comparison to Py and other length values. So there might be a Np and Py L1, L values which will result non-zero value. And as a result, Nb will not equal to 0. Nb is not equal to 0 means that the structure rotates around point B. So it's unstable. This is another example. So as we understand, it is harder to understand if the structure is unstable because of wrong chosen examples. But here, let's think that. Now, I told you memorize one structure. That structure was that one. This is, we have here two members, one hinge here, two simple supports, and this is determinate and stable structure. Now let's come page 36. Same structures, but there is no L shape. It's straight. Two members are straight. One hinge here, two simple supports. But as you will see, this is unstable. So it's not the shape of the members can also make one structure unstable. We can just understand applying this mathematical method if one structure is unstable or not. The shape of the structure is also important. Not only the places of supports, the places of hinges, the shape of the members are also important. Now here I have separated members from their ends and applied external loads. The external loads applied so on the whole structure, you see that, and on the separated structure, the structure separated from the hinge, and the internal hinge forces, reaction forces, and also the external forces which are shown here with green color are also given here, is given here. Now here we will see on the whole structure I write here on this structure, not on that one. Horizontal force equilibrium equation. Px minus Ax minus Bx equals 0. Okay. And then vertical force equilibrium equation. Py minus Ay minus By equal 0. And moment about any chosen point A, MP plus Py times L1 minus B1 times L1 plus L2 equals 0. The system is not externally unstable on the whole structure. Okay. This holds for every time. Why this holds? Because the good explanation comes here. Whatever Px value you choose arbitrarily, Ax and Bx, they are the reaction forces. They are calculated depending on Px. So whatever value Px holds, Ax and Bx get enough values so that the summation of Ax and Bx will result to Px. I mean, reaction forces Ax and Bx will balance the value of Px. I will select the value of Px and the reaction forces develops so that summation of two of them will equal to Px. So this equation holds every time. Here, the same thing. I will select the value of arbitrarily Py, and the reaction forces will be higher enough to make this equation 0. This equation always holds. Here, MP and Py are arbitrarily selected, but the value of Bi, By will balance it. That's why these three equations will always hold. As a result, system is not externally unstable. Whatever value you choose, reaction forces will be high enough to balance the externally applied load, and these three equations will always equal to 0. That's okay. So the system is not external unstable. Now let's, as I said before, write the equilibrium equations separately for each member. From the left-hand portion, okay, Px equal to that. From here, I will get the value of Gx, which is the hinge force. From that equation, you can, on the video, watch and understand how these equations are written. If you look here, you will understand from the left portion. Gy equals to that value. If you write the moment equation about point A, you will obtain Gy equals 0. From the right-hand portion, you will get a value for Gx. This does not tell me anything. Here, Gx equals to Bx, Gx equals to Px minus Ax. This does not tell me anything. Here, Gy equals to that, and here, Gy equals to that. But here, Gy has a specific value, 0, and Py is an external load, and P is an external load, and L2 is a distance, length. They are all positive. So it can be non-zero from arbitrarily by myself chosen Py and Mp values. So Gy shall not equal to 0. I can make it different from 0 value. Here we have two different solutions. This means that system is internally unstable. That's the solution. Now you see, if the shape of this member was different, you see one hinge in the middle and two simple supports, and it's unstable, and to understand that it is unstable was hard, because it's not externally unstable, it's internally unstable. But as you see here, this system is stable. Just these are L-shaped, and the other members are straight members. Now the last topic, let's read here. Even in practice, only concentrated forces are allowed to be applied to the hinge of truss structures. In reality, concentrated moments can be applied to the hinge of the truss structure. Okay, I mean this one in reality might occur. But in textbooks, we see only forces acting on the hinges of trusses. We generally do not see moments, but if I can do it. This might be applied. This can be done. The applied concentrated moments are balanced by the normal forces developed in the truss members and support forces. To check the stability of truss members, first, the whole system is loaded with Pxy and external Mp moment. Equilibrium equations, these three are then written on the whole structure. If equilibrium equations are not satisfied, the structure is externally unstable. If they are satisfied, the structure must be again checked for internal stability. For that reason, the whole truss structure is divided into substructures by using a convenient imaginary cutting line or separating from convenient hinges. It is very hard to understand if a truss structure is internally unstable. Equilibrium equations are then written for every substructures. If equilibrium equations are not satisfied for any of the substructures, the truss structure is internally unstable. If satisfied, the truss structure is stable. The question may arise here as the size and number of the substructures used in the stability control. The answer is as follows. The smallest truss structure is a triangle. Therefore, the whole structure must be divided into triangle-shaped substructures. Nevertheless, checking every triangle-shaped substructure for stability takes a lot of time, since most of the truss structures are composed of many members and hence triangles. In practice, I mean not the truss members, so simple truss members, truss structures, and given in the textbooks or in solving problems, numerical examples. But in reality, for example, you have a roof truss and it has a lot of triangles, and you have to check if it is stable or unstable by means of hand calculations. It will take a lot of time for you. In practice, therefore, special loads are selected with experience and applied to the truss structure for stability. So you can understand if the truss structure is unstable or not with experience. Examples of truss structures that are unstable as a result of incorrectly chosen supports are shown in figures here. For example, here you see I put one external moment here and one external load here, and I choose external vertical load here by experience, by means of my experience. And member forces are internal forces, normal forces, and reaction forces are here. The supports are chosen. So now, first of all, let's calculate the number of equilibrium equations that can be written for the truss structure. As you see here, this truss structure can be derived from one triangle. If, for example, from this triangle, if we add two member, I come here, and then add two member, I come here, and then I add two member, I come here, and I have all of, as you see, I have 1, 2, 3, 4 triangles, and all of the spaces are surrounded with triangles. So there is no problem with it. If I choose I place the supports, choose and place the supports correctly. So number of hinges 1, 2, 3, 4, 5, 6. 6 times 2. 2 is the equilibrium equations written for every hinge. 6 hinge times 2 makes 12. 12 equations, equilibrium equations I can write. Number of unknowns 1, 2, 3, 4. For reaction forces, per member I have one unknown normal force. 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 plus 4 makes 13. Did I do that correct? 1, 2, 3, 4, 5, 6, 7, 8, 9. 9, 10, 11, 12, 13. 13 is higher than 12. So number of support, number of unknowns is greater than number of equilibrium equations. So this could be indeterminate structure. So it's good. It's good. Number of support is more than enough. It's good. But if I have placed the support wrong, okay, then because of wrong place support, this might be the system might be unstable. Now, for the whole system, if this three equation, equilibrium equation, holds for every arbitrarily chosen loading, it's externally stable, and I will check internally if it's unstable or not. Okay. Now externally, I with experience chose those loads, and about point D, I wrote moment equation. Okay. This force, this force, this force, this force passes through all reaction forces, passes through point D. See that? Okay. I have rotated support so that every reaction forces, every reaction support forces passes through point D. So they will not balance the rotation or the moment about point D. So, since L, H are distances, and positive values, and there are plus here, any value of NP, PY, PX will create a non-zero value here. What happens? The structure rotates about point D. The support reactions cannot avoid that the structure rotates about point D. So the system is externally unstable and cannot prevent the rotation about D. Okay? Because of only Px is enough, Np is enough, or Py is enough. I think this is enough. I will not continue, go on. This was a part of my book. So by this way, we can understand if a one-dimensional member structure, truss or frame structure, is determinate, indeterminate, or stable, or unstable. Okay. Please subscribe to my channel. Thank you very much. Don't forget to subscribe to my channel.